Welcome. So this time we're going to talk about digital signatures. Specifically, we're going to get into the El Gamal digital signatures. So let's just jump right into it and let's talk about a reminder about how the El Gamal system works. So the first thing to remember is that there is where there's some things that are shared. So there's shared by everything in the system or by a third party, or even Alice and Bob can each have their own, but the things they have to have is a large prime P and a primitive generator G. So lemon boxes in G and P. And primitive generator, remember, that just means something that creates all the elements in P. It can be whatever I want. Obviously, we don't like one, but like two sometimes the primitive generator, depending on the situation. I'm not recommending two. That's sometimes way too small, but it really doesn't matter. All right, so then Alice comes along. We're gonna put Alice over here, and we're gonna put Bob over on this side. Couple things for Alice. So let's talk first about key generation. So the first thing that Alice has to do is choose some A that is between 1 and P. Technically, sometimes the book allows you to do P or even P minus 1. P minus 1, but it doesn't, there's not really much reason to do that. I would recommend something else, something in the middle, just because it makes it a little bit harder. And then Alice has to compute big A, which is equal to G to the little a, mod P. All right, so with that, and then publish big A, keep little a secret. So little a is secret, big A is public. So that's what happens. So what did Bob do? Well, first one, Bob looks up big A. He looks up Alice and finds out that her public key is big A. Next, he chooses a message M. Now, obviously, we would like M to be smaller than P, because otherwise we kind of lose parts of it when we do stuff mod P, which we're going to do. So that generally is limited by what is our P value that we're dealing with. And then also, Bob has to choose a random element K. Now, what I mean by random element, I'm just going to pick something between 1 and P minus 1, preferably not inclusive again. And then what Bob is going to do is compute two things, compute two values. C1, which is going to be that generator to the K mod P, and C2, which is going to be the message times A to the K mod P, mod P. Now, and Bob is going to send that to Alice. Send both of them. So he has to send C1 and C2 as a combination message to Alice. So why is this important? Here's the first thing that El Gamal is different than RSA. In RSA, we would send one message. Here, I'm sending two. So to encrypt my message, I'm actually having to use two different values. That is where this gets kind of tricky. So next, so this is, by the way, is the encryption process. Let's talk about the decryption process that Alice would do. Well, Alice would compute the following. She would compute C1 to the little a, and then take the inverse of that and multiply that by C2, mod P. Okay, so she has to come over here. She's going to take C1, she's going to take her little a, she's going to raise that power, and then she's going to find the inverse of that value and multiply that by C2 mod P. But why? The truth is, this is going to give you the message because, quick reminder, C1 to the A is really G to the K to the A, which is G to the AK, which is G to the A to the K, and then the inverse of all that. So I did this on purpose because I'm going to go this on just a second, times C2, but C2 as a reminder is just my M times AK, A to the K. But this, as a quick reminder, G to the A is big A. Huh. Well, that means this is going to be A to the K inverse times M times A to the K. So these are going to cancel each other out and just leave me with M when we're dealing with mod P. They're gonna cancel out and we just have to do it. Now we don't actually do this calculations of the things in the middle. I'm showing you the math as to why it works out. In reality, all we have to compute are these parts right here, and that gives me all the way to M, but it's because of this. And the truth is, Elgamal digital signature is very much the same way. I'm going to be sending two things, and it's going to require a strange realization, but the computation is a very straightforward computation. So let me show you what that actually looks like in detail. So first, but let me give you a little quick background. I forgot I want to throw this at you. It was actually created in 1985. So it was created a long time ago. Most of you were twinkle in your parents' eyes. And it is actually the basis for DSA and DSS, two modern digital signature things. They're kind of the standards, actually. DSS is the digital signature standard. They're really common, and they're actually even better than Elgamal because of key length issues. But the idea still is based on this. In fact, I'll show you a little bit later on how Elgamal and DSA kind of compare and show you the slight differences in them. They require us to understand subgroups and some other things like that. And the other reason we started with RSA is because that's way more straightforward. This, again, is not straightforward. You have to be patient. So you're going to want to write this down and kind of ponder to understand why this works. Because the math of it is very beautiful once you understand why it works, because it just doesn't seem intuitive. So let's get into this digital signatures and how it actually works. So again, Samantha for signature is going to choose a large prime and a primitive root G. Both those are still standard from Elgamal. Again, she's going to choose a private key little a and a public key big A, which is G to the little a. So notice, again, all this is following Elgamal. Here's where it gets different than RSA. In the RSA, when you sent something, you looked up the other person's public key and you use that, as well as your private key. That's not really what's going to happen here. Again, she's going to use her own private key. And what she's going to do is she's going to take her document. We're going to call it a document instead of a message, but it's the same idea. And it's going to be an integer. And she's going to compute some k between 1 and p. And notice she's going to do a bunch of calculations here. You already can see there's a little a already involved in this. But there's a couple things that are kind of important in this process that I need to point out. One, the greatest common divisor of k and p minus 1 has to be 1, and I'll explain that in just a quick second. Secondly, we're going to compute S1, which is G to the K. That's really easy. Since we've already done G to the A and G to other things, we know that raising things to exponents in and of itself, when I have the value, it's not that hard. You just don't want to do it a whole bunch of different times. S2, on the other hand, is going to be, I'm going to take my document or message minus little a times S1, which I just computed, times K inverse, but this is K inverse mod P minus 1. This is a critical thing. This is why I had to have the greatest common divisor of K and P minus 1 be 1. That was what guaranteed that there was an inverse. If that number is not 1, then there actually is no inverse and we are stuck and this does not work. So I'm going to take the inverse, but it's mod P minus 1. Well, this over here is mod P. So we have two different mods going on for two different calculations. You have to keep that straight because it's going to be critical. Now, you can think about this for a second. Why do I care about things mod P minus 1? Well, that's because that means that S2 is going to be an exponent. because we love to use Fermat's little theorem to undo and get us out of these situations. All right, so Alice does all of this and then puts out an S1 and S2. So she has worked through this process, and her signature is actually two parts, just like El Gamal. All right, so what happens next? So she has put out there all of her public information about P, G, big A, and also the digital signatures S1 and S2. Even D, you could say, is out there because you could have already sent the message separately, and this is going along with it. So Victor, for verification, is trying to verify D. And so he takes those signatures and he does a couple things. He computes this, which is actually very straightforward. He takes big A, that's Samantha's already put out there on the internet, raises that to the S1, and then takes S1 to the S2. So notice S1 is both an exponent and a base. That adds a little bit of complexity to this problem. So then what? Well, excuse me. It works because of this math. So I'm going to break it down and show you the math, and it's going to rely on the definitions of what S1 and S2 are. So remember, A is equal to G to the A, and S1 is G to the K. Well, that means by the exponent rules, that this is just G to the AS1 times G to the KS2, or we can add them together. But this is where it gets fun. What is S2? S2 is equal to D minus AS1 times K inverse mod P minus 1. So this S2, when I actually multiply it by K, the K and the K inverse are going to cancel each other out in mod P minus 1. So I could have done them separately and then put them back together. But this then gives me G to the A, because remember, the exponent, it's going to mod P minus 1 is when it actually gets to be 0. It gets to be 1. So that's what we care about. Down here, A S1 plus D minus A S1. So the A S1s cancel out and just leave me G to the D. So the things that Victor has to compute, he has to actually do 3 computations. A to the S1, S1 to the S2, and he has to multiply the goes take it back. So that's 3 things. And then he has to multiply G to the D's. He still has to figure out this one. And then he does a comparison. So we have 3 calculations and a comparison to figure out this process. This is the El Gamal process. And let me just show you an example of it. So Samantha chooses the prime P, which is this 21,000. I won't read through all of it. And the primitive root G equals 7. She then picks a secret key A, little a, which is 15,140, and computes big A, which is 7 to the little a, or 7 to 15,140, which comes out to be 17,702 mod P if you do the calculations. All of these first steps are just like all of El Gamal. However, she signs the digital document D equals 5331 using the random element 10,727. And this is how she computes. She takes 7 to the 10,777. That gives her S1, which is 15,775. Mod P. That's the key thing. Remember that S1 is mod P. S2, on the other hand, is going to be mod P minus 1. So first she has to come here and say, what is, when I have this 10,727, what is its inverse mod P minus 1, which happens to equal 6,353. So that's what K inverse is. She already has A, she has D, and she has S1 already previously calculated. So now with all these numbers, she just has to do the calculations in order. She gets 791, again, mod P minus 1. That's the key thing. They're different mods, and you got to keep track of which one's which. I don't have any good tricks on that. So she publishes that along with D, and then Victor comes along. And Victor simply computes big A which is 17,702, to the S1, which is 15,775. I know those sound big. They're really not in terms of the cryptographic world that we live in. Then she again takes, Vector again takes the 15,775 and raises that to the S2, which is 791, and then multiplies those values together to give a total of 13,891. Now, you might be sitting here and be like, Dr. Bailey, something's wrong. And it's because you're not done yet. This value, if you notice real quickly, that is not equal to D. But D, it was never meant to be D. This value right here is a quick reminder. I just didn't have room on this sheet. That's why it wasn't there. Is G to the D. Or in other words, 7 to 5,331 mod P. So if Victor computes this, he should get this a second time. So he does two things. Now here's the problem. Let's talk about this real quickly. What happens if Victor is horrible at his exponent computations? Well, he makes, or he's even using a horrible program and just trusts it and it makes a mistake. It could say that someone didn't sign a document that they did sign because, well, it messed up this calculation. Every single one of these has slight errors. The other problem here is that your private key, you're the key, the key for your signature, the space of it. Your signature has to take up so much space, it kind of just makes this a huge giant muck. And we don't like that. And so that's one of the reasons they actually made DSA actually even better. So it takes up less space, but it's just as much. And just to kind of show you a comparison, on the left-hand side, we have the Elgamal one, and on the right-hand side, we have the digital signature algorithm. You notice that they both start off with a signing key of A, which is between, we start off large prime P, and primitive root G. The difference is that in the digital signature, we also need a Q that is congruent to 1 mod, that P is congruent to 1 mod Q. What does that mean? That means that Q is a factor of P minus 1. But we want it to be a large prime that does that, not a small prime. So we don't pick 2. We pick another really big one. And we want G to be of order Q, meaning G is going to do the number of rotations through, like if I raise G to the Q power, it's going to take me right back to G. So it's going to have Q elements and it's just going to work all the way its way through them every single time. That is the key difference here, is that I have to keep a second Q value, and that's going to end up changing all of these things. If you look, a lot of them look the very same. That again, the signing process is a D and a K. And we have G to the K, and this all looks very similar, except they're both. And for S1, I take mod P, then I take mod Q, and S2 is mod Q. So because I'm actually using a smaller Q value to end up, my digital signature values are going to be smaller, significantly smaller, and thus they actually will take up less space, less bits, and that means it's kind of easier. But you could argue, well, then someone could fake it better, but can they? Because we're still talking about things that are pretty good size. All right, I hope that gives you a basis of this. Good luck. Play around with it a little bit. Go back through that math and make sure you feel comfortable understanding why this works and not just believing me that it does. It's a really beautiful idea of math, and it's one that I think is really, really powerful and helps you start to see that a lot of things you do are not just computation, but we've been learning all these exponent rules over this time, so now we can use them to our advantage to both encrypt and decrypt different ideas. All right, again, good luck. Let me know what questions you have.